The purpose of this lesson is to look at some examples of converting between Cartesian and polar form, or between polar form and Cartesian form. So let's begin with our first example. And the first example is going to be z equals 3 plus 3i. And what we need to do is express z in polar form. Obviously it's already in standard form or Cartesian form, so what we need to do is express it in polar form. Now it doesn't matter how well you know your formulas or how well you think you can do this. Please, every single time, draw yourself a rough sketch. 3 plus 3i. Okay? The most important thing is when you draw your sketch, the sketch helps you identify which quadrant is in, and that will help you work out the angle. Make sure you get the argument correct. Okay, so we've got our quick diagram here. This is imaginary, this is real, our argand plane. Now to express it in polar form, what we want is z equals r cis theta. In other words, we need to know r and we need to know theta. R is this distance, which we can use Pythagoras rule for, and theta is going to be that angle. So r equals the square root, remember, of a squared plus b squared. If you forgot that rule, remember it's just Pythagoras rule. This is 3, this is 3, so it's going to be the square root of 3 squared plus 3 squared, which will be the square root of 18, which is really the square root of 9 times 2, which is 3 root 2. Now if you got your calculator, you could have gotten the square root of 18 and you got 4.24. So sometimes you could write it as a decimal, but I tend to work in exact numbers, in surd form, wherever possible. So there's our r. This distance here is 4.24, which kind of makes sense, because if that's 3 and that's 3, that's going to be just a bit longer, so 4.24 is quite feasible that it's correct. The other thing we need to work out is the argument. Now, first of all, I say let's work out that angle theta. Theta equals the tan inverse of opposite over adjacent. Now, you can probably look at this diagram and know straight away that 3 and 3 is going to be a 45-degree angle. So, but if the numbers weren't quite so nice, then you could do the tan inverse of 3 over 3 or the tan inverse of 1. And just to show you what we'll get here, the tan inverse of 3 divided by 3 equals 0.785. Now that's a decimal that we've rounded off, and once again that would be correct, but I would much rather work in exact numbers where possible. Remember, this is 0.785 radians, because if I go into the setup in my calculator, I've got my calculator angle set to radians. If I change that to degrees, then did the problem, notice I get 45 degrees. So this is 0.785 radians, which the symbol for it is actually a little c, but we don't normally put the symbol for that, or 45 degrees. But in maths, in senior maths, we work much more with radians rather than degrees, for good reason. So I'm just going to go back into my setup, turn my angle back to radians, and I'm done. Now, I'm hoping that you wouldn't actually need your calculator for a problem like this. Tan inverse of 3 over 3 is 0.785, but we know, as I said before, that it's actually, we know it's going to be 45 degrees, and you should know that 45 degrees is pi on 4 radians. If you pi on 4, if I actually work out what does pi divided by 4 equal, you'll find it's 0.785. Okay, because pi is just a bit bigger than 3, and that's 3 divided by 4 is basically 3/4, which is close to 0.75. Okay, 3/4 being 0.75. So I would rather, if you know it exactly in radians, write it in as radians. Okay, so our angle here we know is pi on 4. Therefore our complex number z will equal r, which is 3√2, cis theta, which is pi on 4. So r cis theta. Remember what that stands for. Cis stands for cos plus I sine. This is just a shortcut way of writing 3√2 cos pi on 4 plus 3√2 I sine pi on 4. But we don't write it like that because the whole purpose is to actually write it simply, so we write 3√2 cis pi on 4. There is no cis button. That's not a trigonometric function, cis in itself. It just is short for cos plus I sine. Okay, so we'll do one more example, converting Cartesian into polar form. Let's do this one. Z equals 3 minus 3i. Now, once again, always draw a diagram. Particularly important for a question like this. So 3 on the real and minus 3 on the imaginary. -3. So my complex number is down here. Alright, so we want to know r. R will equal, or r or mod z, same thing. I'm trying to use different notation here just to get you used to it. Mod z or r is the square root of, okay, it's just a right angled triangle, 3 squared and 3. Don't worry about the fact that this is at -3. The length of this line is 3 units long, and you'll save yourself a lot of headaches if you actually just write it as 3 units. So 3 squared plus 3 squared, same as the last example, it's going to be the square root of 18, which will be 3√2. Now, when we come to do the argument here, this time I'm going to label theta there as the angle to the horizontal axis. Now watch carefully here. Theta will be the tan inverse of, and I'm just looking at the lengths. Save yourself some problems and don't put the negative in. This is tan theta is opposite over adjacent, 3/3. Ignore the fact that it's a negative where it's positioned on the plane, and we know already that that's 45 degrees or pi on 4. Now that is just theta. If I was then to write my complex number, and I'm going to write something that's incorrect, if I then said therefore z equals r cis theta, which must be 3√2 cis pi on 4, because that's what I got here, then how is that any different to this previous example we had here? Sorry, this example we had here. It's exactly the same, but clearly the complex numbers are in a different position. The complex numbers are in a different position. So this is obviously wrong, and this is where you need to remember what we were talking about, the argument. The argument must be the angle measured from the positive x-axis with direction included. Now, if we were going to talk about little a arc z, little a arc z would be the angle from here all the way around to here. Now we know that this bit is pi on 4. That little angle there is pi on 4. We know that this, we start off at 0. If we go all the way around, we get to 2 pi. Now if we're working in quarters, we know that 2 pi is actually 8 quarters, or 8 pi on 4. That would cancel down to 2 pi. So all the way around to here would be just pi on 4 short of that. So that would actually be 7 pi on 4. If we went another pi on 4, we'd be up to 8 pi on 4. However, this is little a arg z. That's the argument of z with the little a. However, what we've said before is that we like to work with big A arg z. Now big A arg z, remember what we in a previous lesson we were saying needed to be the shortest distance to get to the complex number. So if we start, remember our starting point is always the positive real axis. What's the quickest way to get to here? Well, it's not going all the way around the circle, it's actually coming back this way, coming backwards. And when we're coming this way around the circle, our angles are negative. So coming this way, we're going pi on 4 in the negative direction. And so capital A arg z is just negative pi on 4. That tells you come backwards around the circle. Therefore, our complex number is r, which is 3 root 2, cis negative pi on 4. And then it's clearly different to this one that we did over here, where the argument was positive pi on 4 because we went upwards. Alright, I'll do one more example to help us with this. Okay, the example we'll do now is z equals negative 3 plus 3i. In fact, I may do one more after this one. Okay, so in this case, negative 3 plus 3i, and you'll see that I'm doing very similar numbers each time to help you see the difference. Negative 3 plus 3i. Always draw a diagram. Negative 3 on the real and plus 3 on the imaginary. There's my complex number. So what I need first of all is mod z or r, same thing, you don't have to write both. Mod z would be this distance, this length is 3, this length is 3. So it's the square root of 3 squared plus 3 squared, which will be square root of 18, same numbers as last time, which will be 3 root 2. No problem there working out r. Now, we always work out the angle to the nearest horizontal axis. Okay? We don't want to work out this angle in here. Okay, we'll never be working out that angle in there. We always want the angle to the horizontal axis. Okay, so now we can work out theta is the tan inverse. Now, like I said last time, forget the fact whether it's positive or negative, just work in lengths. Your calculator won't know which quadrant you're working in if you use the plus or minus signs or the negative signs. So just work out the tan inverse of 3 over 3, the actual lengths of those sides. We already know this one is pi on 4. Now that's only this angle here. We want capital A arg z. Capital A arg z is always measured from the positive real axis, and it is the quickest way of getting here. So the quickest way of getting here is not coming backwards this time. We don't want to come backwards because that's further than it is to come this way. So we're going in the positive direction, that amount. Now, I'm not sure how familiar you are with doing this, but this is how I work it out. This is pi on 4, that angle in there. I know this is pi. Okay, pi is 180 degrees. So, or, since I'm working in quarters, I like to convert this to quarters. It's going to be 4 pi on 4. Then I can see, well, this is pi on 4, so I'm not quite up to 4 pi on 4, I'm 1 pi on 4 off that. So this angle around here is going to be 3 pi on 4, so that becomes my principal argument. Therefore, Z equals R cis 3 pi on 4. Okay, I'll pause the video here and I'll do a couple more examples in the next one.